We are going to study modern electronic theory of magnetic properties of the materials. Magnetism is one of the Earth's mysteries. Magnetic materials are all around us and play a very important part in our modern world. It is difficult to imagine a world without magnetic materials, and they are becoming more important in the development of modern society. And we are going to see what is meant by magnetism, what are the atomic reasons for magnetism, how are the magnetic materials classified. Magnetism is a phenomenon by which material exerts either an attractive or repulsive force on another. The magnetic field is produced by a, when a current is flowing in a conductor, or you can say when there is an electric charge in motion. In the case of materials, magnetic properties originate from the motion of their electrons and their magnetic moments. The origin of magnetism in the case of material is due to the magnetic moment due to orbital motion of electron and magnetic moment due to spin motion of electron. Nucleus also contribute towards the magnetic moment, but they are much smaller than spin. It can be ignored. Let us say the basic definitions based on which the materials can be classified. The important one is the magnetization. It is a measure of how a material responds when magnetic field is applied to it. Then magnetic susceptibility. It is defined as a ratio of the magnetization to that of the applied magnetic field. Then there is a magnetic permeability, and this all the three are the basic quantities based on which the materials can be classified. There are certain material which contains even number of electrons, and based on Pauli's exclusion principle, the resultant magnetic moment is zero. They are grouped in pairs. There are certain other material in which there is a net magnetic moment, and depending upon the net magnetic moment present in the material and the alignment of these magnetic moments in the presence of applied magnetic field, metal can be classified into dia, para, ferro, antiferro, and ferrimagnetic materials. Let us start with the diamagnetism. It is a very small and very weak effect present in all the materials. It is an inherent property of all the materials. It is caused by the reaction of orbital electrons to an applied electric field. So when you look into the properties, this diamagnetic susceptibility, which is magnetization upon applied magnetic field, it is very negative and very small. Examples for this is copper, silver, zinc, silicon. When this material placed in external magnetic field tend to move from stronger part of the field to the weaker side. And the permeability is also negative, and it is masked by the other magnetic effects. When placed in external magnetic field, a tendency to repel away the magnetic field lines. And this main thing is when you talk about the magnetism, we have to talk about the spin as well as the temperature dependency. It is independent of temperature. When the next type of magnetism present in the materials like aluminum, chromium, zinc, etc., the paramagnetism, it is exhibited by the materials having unpaired electrons. They possess permanent magnetic dipole moment, and susceptibility is small and positive, and placed in a external magnetic field, it moves from a region of weaker side to the stronger side. It allows the magnetic lines, when it is placed in an external magnetic field, it will allow the magnetic lines to pass through it, and the permeability is greater than 1. And this type of this magnetic susceptibility of paramagnetic materials is dependent on temperature. It is chi is it follows chi is inversely proportional to temperature. So when the temperature is this is called as Curie-Weiss law. Later we will discuss this in detail. There are materials like iron, boron, nickel. They possess spontaneous magnetization. What do you mean by that is there exists a strong interaction, a spin exchange interaction between the adjacent dipole, and that is confined to this small region, very small volume called domain. And because of that, they exhibit spontaneous magnetization even in the absence of external magnetic moment. So they possess net magnetic moment. When such a thing is placed in external magnetic field, they tend to align. It will give us a very large magnetization, There's all this domain as the strength of the magnetic field increases, the domain are parallel to that of the external magnetic field, and of material is antiferromagnetism, and it's exhibited material oxides of iron, manganese, chromium, etc. and transition elements, they exhibit this property. Here the spin, when you see the spin, they are equal in magnitude and opposite in direction. So this net magnetic moment is zero, and it is also a temperature dependent. The next fifth kind of materials, the ferrimagnetic materials, or you can call it as ferrites. Examples: ferrous, ferrite, nickel ferrite. And this is a special type of antiferromagnetic material, wherein this, when you see this, their spins are unequal in magnitude and also opposite in direction. So they give rise to very large net magnetic moment. That susceptibility is very large, and as well as it is positive. So to put it in a nutshell, when you take a diamagnetism, they are exhibited by the materials having even number of electrons, no net magnetic moment. When it is subjected to applied magnetic field, the electrons, the motion of electron will get modified in a direction opposite to the direction of the applied magnetic field according to Lenz's law. Next comes is paramagnetism, which contains random alignment of net magnetic moment, but spins are oriented in random direction. When it is subjected to external magnetic field, there will be alignment of magnetic dipoles along the direction of the magnetic field. Next comes this ferromagnetic. Ferromagnetic, it exhibits a large spontaneous magnetization, large magnetic moment, but when it is subject wherein the spins are this parallel to each other as well as equal in magnitude. And this ferrimagnetism, they have got domains. They are oriented in random direction. When it is subjected to applied magnetic field, they tend to align themselves parallel to that. They will give rise to net magnetic moment at a very large net magnetic moment. But in the case of ferrimagnetic moments, the spins are unequal in magnitude as well as opposite in direction. To put it in a nutshell, the diamagnetic materials, when it is placed in an external magnetic field, it will not allow the magnetic lines to pass through it. Paramagnetic materials, it will allow the magnetic lines pass through it, and this paramagnetic materials, it will allow more number of lines to pass through it. And when you study the temperature dependence of susceptibility, in the case of diamagnetic material, they are independent of temperature, and in the case of paramagnetic material, susceptibility is inversely proportional to temperature. In the case of ferromagnetic material, this susceptibility follow the relation Curie-Weiss law. So there is a particular temperature called ferromagnetic Curie temperature, and below which the material exhibits ferromagnetic property, and above which when the temperature reaches beyond that, it becomes paramagnetic. That means it will align, it will lose its alignment, it will become random alignment. And in the case of ferromagnetic materials, again in the case of antiferromagnetic material, there exists what is called as a Neal point, and below which they exhibit antiferromagnetic property. That means the spins are parallel to each other and opposite in direction. Once the temperature exceeds the Neal temperature, this antiferromagnetic property behavior will tend to again paramagnetic. So when you classify the materials, the two important points you should keep it in mind. One is how the spins are aligned, and what is the dependence on temperature, that we should keep in mind. So it is difficult to imagine a world without magnetic materials, and they are becoming more and more important in the development of modern society. To cite some examples, diamagnetism, it is materials, they are employed in magnetic levitated train, growth of floating crystals in a way using a powerful magnet. Paramagnetism, paramagnetic materials, they are used such as chemical species with unpaired electrons such as oxygen. They exhibit paramagnetism in the presence of external magnetic field. It is used in oxygen analysis. Ferromagnetic materials, they are employed in electric motor, generator, transformers. In the case of medical fields, we are using it in MRI scans, CT scan, DNA sequencing. Antiferromagnetic materials, they are used in magnetic sensor. Ferrites, are ferrimagnetic materials. They are used in electronic industries to make efficient magnetic cores for high frequency transformers, etc. To summarize, magnetic field can be produced by putting a current through a coil, and magnetic induction occurs when a current material is subjected to a magnetic field or there is a change in the magnetic moment from the electrons. So based on this, we can classify this magnetic material into dia, para, ferro, ferri, and antiferromagnetic materials. Hope you have understood. I have placed certain questions. Try to answer this. Thank you.